Up next, we have Robin David. He is going to be presenting on something that I found truly inspirational, because I don't know how many people out here have had to reverse engineer not just a single binary, but a whole system of binaries. So not just one, but when you have to reverse engineer across an entire system, things get very complicated, and pretty much all of the tools kind of fall over in that situation, Binary Ninja included. But Robin's come up with some really cool stuff that means I have to do a lot more work. But take it away, Robin.
All right, so welcome everyone. I'm very happy to be here for the first edition of Reverse. And I will be presenting some research work that I've been doing to facilitate the reconnaissance phase when you come up with a whole file system, basically, so that you can quickly pinpoint the interesting binaries that are of interest, so that you can get proficient on them. Very briefly, so I'm Robin David. I've been working at Quokka for the past 8 years almost. And my topic of interest are quite wide. I do a lot of obfuscation, fuzzing, symbolic execution, all what relates to graphs, and the topic of today, firmware analysis. Just a quick recap of what will be the kind of firmware that we are going to tackle today. I distinguish two main types of firmware. The flat firmware, where you basically have just a segmentation of the memory. It applies for most of the small MCUs and things like that. And on the other hand, there is what I call the structured firmware, where ultimately you have a kernel and a file system. You might have multiple partitions, but yeah, the idea here is that we're going to focus on big firmware that have a whole file system into them. Why we tackle this kind of firmware? Because this is the things that you will encounter when you do vulnerability research. Whenever you have a firmware, you will have to deal with multiple files and executable. And there is the reconnaissance phase that indeed you have to do when you are given a file system. Whether it's for compliance or vulnerability research, you will have to basically understand how everything is architectured. When you have to do some firmware analysis, the first two phases are the acquisitions, so you can either dump it from the flash, or you can put yourself in the middle of an update or something like that. And then usually you have a binary blob that you will have to, for which you will have to extract the content. It could be proprietary, which can be problematic. But if everything goes fine, in the end, what you obtained is a file system with the different partitions. But today's focus will be on what we can do with that. Because, yes, as I just mentioned, we have to do some mapping, cartography, to basically understand who is using what, which binary is using which libraries, how a given file is being consumed by an executable, for instance, so that you can do all your security or compliance checks. So the problem is, OK, you extracted a whole file system. You have thousands of executables on files. Where do you start? It's really like finding the needle in the haystack of binaries if you're looking for vulnerabilities, for instance. So the idea for us today will be to map these dependencies between binaries into a graph that you can explore. And I will show you how to do that with a bunch of tools for which most of them we wrote. So no rocket science here. It's just assembling some pieces together so that you can facilitate your reverse engineering tasks. The questions we usually ask ourselves when we have a firmware is OK, I have these functions. Who is calling it? Who is using that file? Who is interacting with such or such daemon? Yeah, this is the kind of questions we ask ourselves usually. And there's a small example here Ideally, you have a function, for instance, of OpenSSL, verify final, and you want to know what are the binaries that are calling it. Because if, for instance, you're interested in checking the firmware signature checks, this is the kind of functions that you might end up looking at. And this is basically the kind of graph that it ultimately wants to be manipulating. So what we propose here is a fractal approach where we start from the level 1, which is going to be what we call the call graph of the whole firmware. So I'm going to show how we compute that. So that will give you the broad overview of the firmware. But then you might be interested to dig into one binary. So in that case, you will be able to manipulate its call graph. And we will add some decompilation features to it. And the last level is indeed your favorite disassembler. There's nothing like your favorite disassemblers to manipulate the data structures and so on. So the first level is what we call the inter-image call graph. And this is basically a call graph, but where the nodes are the functions and the edges are the calls. But the functions are, the graph it contains all the functions regardless of their locations in the binaries. So there's some kind of requirements that you have to put yourself into. You have to have the file system in kind of its running state, so you might have to handle the mounting points and things like that. And you're somehow doing the work of ld.so if you want to know like which function is being imported by such or such program. And we find out that there's no tools or that compute such representations. So we decided to do it. I'm not going to dwell that much into the details of how to implement that. I'm just going to highlight the few constraints that we have. So indeed, you might have some collisions because you import a symbol that is being exported by two different libraries. We have edge cases. For instance, we found like in some HTTPD modules that the modules were importing functions which were not exposed by any other libraries. And indeed, when you compute that graph, what you want to do is to, in the ELF format, for instance, you have the PLT mechanism that allows to jump in the target functions. We don't want to have this trampoline jump, so we want to bind directly the call to the target functions in the library. How we are going to do that? We're going to feed all the executables in a disassembler. It can be the disassembler of your choice. And where we are, what we propose here, the pipeline that we propose is that we are going to export the disassembly into an export file. It basically allows us to manipulate the disassembled representation offline and be kind of independent from the disassembler that generated it. So for doing that, we are using Quokka, which is our own exporter. Then you are going to feed that to an indexer. And ultimately, you want to store that in a graph database. And here we're going to use the graph database of Sourcetrail. I'm just going to describe it a bit more right after. And to do that, we're going to use a small library, which is called Numbat, which is going basically to provide you an Python API to create this database. And we try to automate the whole process so that we can just launch it, come back a few hours later, and then you have your graph ready. So very briefly, for people who don't know Sourcetrail, it's a very great tool. It has been designed to navigate huge code bases. I think it was made by some ex-Googlers that had to deal with like the Chrome code base. Unfortunately, the project has been abandoned. But the good news is that it's open source. So here you can see that you see on both sides of the tools, you have both the graph where you can see the codes between the functions, and you also have the source code that you can navigate into it. So that's a very convenient tool to use. And historically, it has been designed to index C, C++, Java, and Python. Right, as I mentioned, the database format is somehow open source. So if we are able to make any arbitrary data to fit into this graph database, we should be able to navigate this data by using the Sourcetrail GUI. So that would be awesome. And this is actually exactly what we are going to do. So we implemented a small Python API, which is called Numbat, that does just do that. So the idea here is that we really want to bring back some reverse engineering tooling back into source-based tools, which are kind of mature when it comes to navigate, for instance, source code. So I will just give you a small demo of, I'll skip all the indexing phase. So here I indexed a Netgear router. What I have here is 565 binaries. And I can just take any of them. We see that there is 500 functions. So we have the functions with the symbols, but we also have functions which don't have the symbols as they are given by IDA. And then we can travel around into the call graph across all the binaries. This one might not be a very good example, but yeah, let's take, I don't know, this one. We can see that it's using different shell libraries. And if I take a random function, yeah, not fancy example. I will start with the libc, for instance. If we want to, oops. If you want to see like all the functions that are calling execve, you can just select the functions, and here you can see that it's being called by some shell libraries and some other binaries, all right? So you can just travel into it. You might be interesting to like see who is doing like syscalls, so you would be interesting to look at the A2I, and we have like 100 of them here. And the interesting here is that you know exactly which function is calling that. So you can relate to it if you're interested. And I will illustrate a small example here. If you have a firmware that is going to fetch some content with URL, if you were to do it on the command line, you would do curl and your URL. But if you do it through a program, you're going to use the C library, and you're going to basically do the exact same thing here. But the thing is that if you want to make sure that you're going to do the certificate checks, you have to set some options before doing the query. So here, the verify host and verify peer have to be set to 1. And these two enums are 81 and 664. So here we can very easily check that function. Oops. Sorry. Okay. There we go. We have 10 binaries that are using that function. So yeah, it's quite fast to have it. And we have a library here which is interesting, which is called libfirmwarecheck.so. And it's the function curl post that is calling it. So we can bounce back on curl post, which is itself called by 2 other functions. Here you can leverage the features of Sourcetrail to basically do multiple hops. So we can do like 5 hops back from curl post. And we can see that it's being called by this function, which is itself is called by this function, which is exported and called by pucfu and another binary here. So that gives you really fast, meaningful information to know who is calling what, okay? But the thing is that here we don't know how the function is being called, if it's called with the right parameter or not. So this is where we're going to go one step deeper. And because we are using a source code tool, we might want to try to fit the decompiled code into it. And this is exactly what we're going to do. And the thing here, in existing disassembler, it's sometimes a bit complicated to like navigate in both the source code and the cross-references to some functions and so on. While it's perfectly seamless here if you do it with a GUI like Sourcetrail. You have the graph on one side and all the cross-references on the right, okay? So the question is, can we do that with the decompiled code and try to make everything to fit into it? The answer is that yes, it's doable. So the pipeline here will be kind of similar, except that we are going to, in addition to the call graph and the disassembly, we are also going to decompile the whole program, and we are going to feed that to an indexer to build a database. A bit of free rant against IDA here. HIDA is really not of any help for putting the source code into Sourcetrail because we want to somehow be able to tokenize back the calls within the, the lines and columns within the decompiled code. So today we are doing it a bit of in a hacky way. And there we go. We are going to check that. So I indexed lib firmware check.so. So here we only have the 200 functions. And if we click on any of them, we can see the code and all the cross-references that we have into it. So for instance, this function is being called at 13 locations, and you can basically look at all of them pretty much like you would have done it from the source code, right? So let's go back to our use case here. We want to know how curl easy setup is being called. Oh, sorry. There we go. Okay, and yeah, as again, it was called by curl post, and we can see here that's being called with various parameters. And the bad news is that the verify peer and verify host are set to 0, which means if we go back to the previous representation, that PU, CFU, and caller binaries are without knowing, making URL queries without checking the certificates. And basically, so you can man in the middle and so on. So yes, that's the second stage. But obviously, looking at the decompiled code and the call graph might not be sufficient. So indeed, you might be interested to still open your disassembler to do some scripting, manipulate data, and do anything that you are comfortable with. And just to facilitate our lives here, we just added a small feature here where we right-click, say open with HIDA Pro, and it will just open HIDA and jump right into the function. So you can, in the third level, get back to your disassembler. Yes. So rather briefly, so here we've done that on Linux-based file system, let's say. But I want to highlight the fact that we can apply the same methodology with any kind of format where there is binaries that are somehow linked with each other. And a good example for that is the dylib shared cache of Apple devices. Very briefly, the dylib shared cache is pre-linked. It's a huge binary blob made of pre-linked share libraries that is going to be mapped in memory, and so that many executable will be able to use it. But there is some issues that are raised to index this file, which are specific to the Apple ecosystem, because they have multiple mechanisms like stub libraries, function re-export, the symbol coalescing, and the stub islands that you might have to handle if you want to properly build this call graph, this inter-image call graph. The function re-export is basically the mechanism where a library might expose the functions for which it does not have the implementation, but the implementation lies in another library. So here, once again, we have basically the same pipeline, but here we are going to leverage IPSW, for which we are going to feed it IPSW file. We're going to use the split to create a macro for each libraries that are contained into the shared cache. And then we are back into a more similar mode than we were previously with a standard file system of Linux. Except that we have to handle all these specific things. Right, I'm not going to do the demo, but I will just highlight some facts here. I took an arbitrary shared cache here, which was more than 3.4 gigabytes big. So we are now on another scale in terms of binaries. We have 2,500, so it's kind of a lot. And so we have millions of nodes and edges. So when you open it with Sourcetrail, it's really, really slow, and you have to wait a bit to navigate into it. Because indeed, we are hacking somehow Sourcetrail, and it probably was not designed to handle such a a huge load of nodes because of the internal model, SQLite model that they are using. Yes, I didn't mention it, but the graph database that they are using is in fact a SQLite database. All right, I will jump to the conclusions and takeaways of this presentation. So what we proposed here was inter-image call graph representation that maps overall call graph of the whole firmware. We propose a nested graph methodology approach where you start from the firmware, then you jump to one binary, and then ultimately you end up in your disassembler. So for the reconnaissance phase, it's kind of useful because you want to go from broad to specific, indeed. And here, I mean, I used IDA because I'm used to that, but you can completely switch it to your favorite disassembler. But here we've just shown you how to like assemble some tools to build that. And the tools that we developed in our case here was the Quokka exporter, the Numbat Python API, and some tweakings in the Sourcetrail GUI. All that, just to recall, was a goal to bridge like the gap between reverse engineering tools and the source code audit tools that would deserve to be blended in a more symbiotic manner. And why we did that? Obviously, we want to be able to manipulate and travel around multiple binaries all at once, so that we can have the big picture of the firmware. And indeed, we do that to be more like efficient in our reverse engineering task. A few words about the code itself. So it's still a bit in a like proof of concept state. And we're in the process to integrate it in another of our tool, which is called Pyra, that we might publish that like somewhere around June, I would say. But we have to polish a lot of things. But I think here we just map the calls. We could go way further into that by mapping types, data, and so on. So there's a lot of things that could be done by leveraging a Sourcetrail. And there's multiple use cases that here we just map calls, but you can map like inter-process communications if you do some reverse engineering of them, like interactions between like, I don't know, security levels between kernel and user land. You can map permissions with that. You can, I mean, and that will be my conclusions. Anything that you can model as a relationship on a graph, you can basically make them to fit into a graph database by using Numbat and then to have a nice interface to travel into it. And that will be it for me. I'll be happy to take any questions that you might have.
Does Sourcetrail allow querying of that data? Like, could you have queried for those arguments in the curl call?
No, no, you cannot. But what you can do that I did not mention here is that you can use the full text search of the SQLite database. So here, if I do, oops, like, oh. For instance, URL, damn it. It will do a full text search into the decompiled code. So here I just typed URL, so I can see all the strings where that keyword happens. And then, yes. So here it's purely a feature of SQLite that you can use through Sourcetrail. In fact, yes, you can. If I'm looking, if I change that query with, I would say 64, something like that. Yes, I end up, you somehow can do that.
Any more? All right. Thank you, Robin.
Thank you.